So welcome all. As Paul said, I'm Andrea, and I'm a PhD student at Qilimanjaro Quantum Tech. And today I will talk to you about our work on building an analog quantum processor based on coupled Fluxonium qubits. And well, I'm sure you are all familiar with these expressions here on screen. So on top we have an Ising type Hamiltonian, then we have a transverse field Hamiltonian, and finally we have a schedule that gradually brings you from one Hamiltonian to the other. And this, of course, with some other details, it's indeed a really powerful algorithm that can be used to solve a wide variety of optimization problems. However, as I'm more on the experimentalist side, I'm more interested in answering the question on how can we physically implement this. And within the wide world of superconducting circuits, a natural way of doing so is by using the so-called flux qubits. And this is actually the scope of this talk, to introduce to you how can we build an analog processor based on this technology, in our case, based on Fluxonium qubits, that is able to implement this kind of algorithm. And for this, I have organized the presentation as follows. First, I will introduce to you what are Fluxonium qubits, and I will try to explain why they are well suited for implementing these kind of algorithms. Then I will introduce how can we couple Fluxonium qubits, and I will show to you our proposed coupling scheme, and I will also show some of the results that we have already obtained. And finally, I will give the conclusions and outlooks of this work. So, okay, what are Fluxonium qubits? Here on screen, you have an example of a Fluxonium qubit. And Fluxonium qubits consist of a Josephson junction that in this diagram is depicted by this box with a cross, that is connected in parallel with a capacitor that you have here on top and an inductor that you can see at the bottom. This inductor is usually built from an array of Josephson junctions, or it can also be built from some material with high kinetic inductance, such as granular aluminum, for example. And what interests us about Fluxonium qubits is that when we thread their loop by an external magnetic flux of a value half an integer flux quanta, then the system exhibits two degenerate ground states that represent currents circulating in opposite directions in this loop. And these are what we call the persistent current states of the qubit, and in this diagram, they are represented by these left and right states. And then we can express the two lowest energy levels of the system by means of a symmetric and an antisymmetric superposition of these two states. And in terms of potential, this translates into a double well potential, as the one that you can also see here on screen. And each of the persistent current states is associated to one of the wells of this potential. Remember that this happens at this point that I was talking to you, this half an integer flux quanta point, that we also call the sweet spot of the qubit or the flux degeneracy point of the qubit. Because if we move from this point, then the potential gets tilted, and one of the states becomes more predominant depending on the depth of these wells. And well, this is until we eventually lose this double well behavior of the potential. And we usually represent this difference in depth in the wells by an epsilon parameter, and we also represent the tunneling between the two wells by this delta parameter that you can see there in the diagram. And this allows us to represent a system of coupled flux qubits by means of an effective potential as the one that an effective Hamiltonian as the one that you can see here now below on screen, where the first sum corresponds to the single qubit terms, while the second sum describes all the possible pairwise interactions between the different qubits. And from this expression, it becomes quite clear that with a system like this, we have all the necessary ingredients to perform an algorithm as the one that I was talking to you in the first slides. We even have more coupling terms given in this expression, that if, of course, at some time we're able to control and to manipulate, this could lead to potential speedups in our computation, or even would allow us to simulate much more complex systems. But I mean, this is out of the scope of this talk. And what interests us about Fluxonium qubits is that when they are operated at this flux degeneracy point, they become quite insensitive to flux noise, and they also exhibit large harmonicities. And all these properties give Fluxoniums very long coherence times. And this has made Fluxoniums really promising candidates to build quantum processors. And this is why the community has been lately focusing a lot on studying this kind of qubits. And this is also why, if we look into literature, we can actually find many different studies on coupled Fluxonium qubits. Here are some of the examples that we can find in literature, and we can see that people have been trying to couple Fluxoniums both capacitive and inductively, either in a direct way or in an indirect way, just by using couplers. And what happens with these coupling schemes here is that most of them are optimized for digital computing, and this is why they lack some of the properties that one would like to find in an analog processor. And having this in mind, we decided to take some inspiration in these previous studies and try to propose our own coupling scheme. We wanted an inductive coupling scheme, as I mentioned before, because our first goal was to try to have a system that was able to run this type of algorithms. And we came with this circuit here. While we were thinking about this, we had in mind that, as I mentioned, we wanted a system that was able to have some tunable inductive coupling. That is why we decided to couple two Fluxonium qubits by means of a tunable coupler that is, in its turn, a Fluxonium-like circuit element. We decided to make this coupling between the Fluxoniums and the coupler to be galvanic, and this means that the Fluxoniums share a line with the coupler, and in this case is this line where you can find the inductor LC. And we did so because we were looking for a system that was able to achieve coupling strength in the order of the qubit gap. And for this kind of qubits, you need to do this kind of couplings in order to be able to achieve this range of strength. And finally, we decided to build a system that was free of ground loops in order to avoid trapping flux. And this is why our circuit is floating. And well, this system might look a bit complex at first glance, but it can actually just be described by means of 4 different modes. And we have 2 Fluxonium modes that in this diagram are represented by this θ1 and θ2 that represent just the difference between the 2 nodes corresponding to each Fluxonium. So it's basically the phase through the squid loop. This is something that maybe I should have mentioned, that it's important to notice that in this circuit, we decided to replace the single Josephson junctions of the qubits and the Fluxoniums. Maybe in the previous slide you can see it better because it's indicated there. We replaced this single junction by 2 junctions in parallel, and this is called a squid loop. And we decided to do so to add extra tunability to our system because, as I mentioned before, by tuning the flux in the main loop of the qubit, that it's usually called the Z loop of the qubit, we're able to tilt its potential. But with this extra loop, we are also able to tune the height of the barrier between the 2 wells. So this is why we decided to add this extra feature to our circuit. And well, sorry, as I was mentioning, to describe this system, we can use the 2 Fluxonium modes that are just the phase through this squid loop. And we can also use 2 coupler modes. The first mode, that is this θ plus mode, that is the sum of the 2 node variables. It's just a purely harmonic mode of the coupler. And then we have this θ minus mode that, again, it's this phase through the squid now of the coupler, and it's a Fluxonium-like mode. And this means that it's flux tunable. And the interesting thing in this system is that the interaction, it's not directly through the Fluxonium modes, but it's mediated through the coupler modes. So when you compute the coupling strength of this system, it actually has two contributions. One contribution that comes from this interaction between the Fluxonium modes and the coupler harmonic mode, and another contribution that comes from the interaction between the Fluxonium modes and the coupler Fluxonium-like mode. And these contributions actually have opposite signs, so this allows us to tune the coupling strength by tuning the second contribution, the one with the coupler Fluxonium-like mode, that it's flux-tunable, as I mentioned. And we can even get to a point in which the interaction is turned off when these two contributions get the same magnitude. But this will become more clear in a while, when I show you some more slides. And well, the question now is, what do we do with this circuit? Because remember that our goal was to be able to fabricate a circuit that we could later measure in our lab in order to implement these algorithms. So what we did with this circuit, I won't go into all the details because this would take probably another talk, but we followed this pipeline here in which we took the circuit, we used circuit quantization techniques, which is quite a standard method in order to achieve a Hamiltonian that could describe it. This Hamiltonian had both a non-interacting part and an interacting part, and then what we did with this was to diagonalize this Hamiltonian, both the non-interacting part and the full Hamiltonian, in order to achieve an energy basis that could be used to apply the Schiffer-Wolff transformation to obtain this effective description that we were looking for. And this effective description is the one that we simulated, and this allowed us to obtain a set of parameters from which we could build this physical circuit that we were looking for. While doing this, of course, we realized that in our first model, we were actually lacking some of the parasitic capacitances that arise in a real physical device, and that they come just from the different geometry of the different elements in the circuit. So that's why we decided to include them before moving further on, and our circuit became something like this, which now it's, of course, much complex, but luckily can still be simulated using the same 4 nodes modes as before, and again, following the same pipeline, we were able to obtain an effective Hamiltonian that we could simulate. And this allowed us to obtain this set of parameters that we wanted, and we were finally able to actually build our own circuit. These are some microscopic pictures of our device that has been recently fabricated and that we have started measuring, which is something really exciting. We started measurements recently, so I still don't have results on that. We will have them soon, probably. But that's why I will focus the remaining of the talk on explaining to you some of the characteristics that we expect for this circuit that we obtain from the simulations of this effective Hamiltonian. And the first thing that I want to show to you is that we managed to separate the energy scales of the Fluxonium modes that you can see here on the right, and the energy scales of the coupler modes that you can see there. And this is really important to have this separation because you want your coupler to remain in its ground state. And we were able to achieve larger characteristic energies for the couplers, as you can see in these plots. Of course, ideally we might want a bigger separation between these two energy scales. But we were not able to achieve this because we weren't able to get larger charging energies for the coupler, and this was due to all these parasitic capacitances that we have in our circuit that, as I mentioned, just come from geometry. So this is something that we want to improve for future prototypes, maybe slightly changing the geometry of the circuit. We also have other ideas, but this will be further studied on. But yeah, for a first prototype, we were happy enough. I mean, the two energy spaces are well separated, so this is a good indicator. Another thing that we could do from this effective Hamiltonian was to compute the Pauli coefficients, both of the individual qubits and also of the interactions. Here, for example, you can see these Pauli coefficients while sweeping the Z flux in the first qubit. And what we can extract from these plots is that we actually have an independent control of these Pauli coefficients. And I'm saying this because if you look at the first plot, the one that it's here, you can see how while we tilt the qubit, the interaction strength remains constant, which is, you can see my mouse, but it's in the, yeah, maybe this works, no? Which is in that plot here. And another important thing here to notice is that the coupling strength that it's dominant is this Z-Z interaction that we were looking for. Remember that we were looking for inductive interactions, while the other two remain almost zero as we wanted from design. And another thing that we can do is to compute the spectra of this system. And here we have represented in solid lines the energies from the interacting system, and in dashed lines the energies from the non-interacting system. And the important thing to notice here is first that the 4 first energy levels are well separated from the 5th one. This is something that you want because remember that our computational space are these first 4 energy levels. And another thing that we can extract from this plot is that we can observe between the first and second level this characteristic avoided crossing that you can find in coupled systems. And that actually later in measurements, you can use this kind of plots to extract the actual coupling strength of your system. And I guess it's something we will do later on. And now, if we move on to explore the behavior of the coupler, we can again compute the Pauli coefficients, but now sweeping the Z flux of the coupler. And here you can see that if we look at the third plot, which represents interaction, as I was mentioning before, we have both ferromagnetic and antiferromagnetic interactions that are tunable with the flux of the coupler, and we even get to this point here, and this which is like symmetric, in which around 0.3 in flux, in which we can turn this coupling off as we intended. And another thing to maybe take from here is that we can see the huge impact that has threading of flux in the main loop of the coupler, because you can see that the qubits actually shift a lot. And I mean, this is expected just because of having this galvanic connection in the circuit, no? So if we thread a flux in the main loop of the coupler, of course, we're generating a current that affects the qubits just because how they are connected, no, to the coupler. And this, of course, can be mitigated, it can be calibrated. In a system of 2 qubits, maybe this is doable. Of course, if you move to higher dimensions, this becomes quite intractable. And this is actually why we decided to include this squid loop in the coupler, because what you can do then is to fix the flux on the main loop of the coupler and tune the strength just by threading flux in the squid. And we are able to achieve the same range of tunability, and the qubits remain almost they don't move, no? So they remain constant, which is the purpose of this loop. And with this, we get to the end of the talk. So we were able to study the behavior of a system of coupled Fluxonium qubits, and this allowed us to develop a model that could be used to simulate the system and to get to a set of parameters that later allowed us to design an actual physical circuit of this system that we could fabricate in the lab, and that is currently being measured in our lab. And of course, this is a first prototype. There are some improvements that we have to do We already have spotted some of them. We might spot more once we start measuring more these devices. And these are like the next steps that we want to follow. And well, this is our team in Qilimanjaro, and thanks for your attention.
Thank you, Andrea. Are there any questions?
Hi, nice talk. What is the maximum coordination number that you can generate using this kind of a coupler?
Can you repeat, sorry?
So what kind of coordination numbers for your qubits? Like how many qubits can you connect one qubit to by these kind of coupling schemes?
Okay, I mean, right now, our prototype, it only has 2 qubits. I mean, it's the first prototype. But the idea, we are also studying on building an hexagonal lattice made from these kind of connections. And yeah, so this is our goal for the moment.
So one other short question. So you deliberately chose a ZZ interaction between the 2 qubits, but could you choose situations where you get everything and tune that?
I mean, everything, I see for the moment, I mean, in this system, what it's easy to obtain, it's obtaining a tunable ZZ, as it already has, and probably a fixed YY, because it's easy to generate this capacitance interaction just by placing the capacitors of the 2 qubits probably closer to each other. Of course, this will be fixed, not tunable, but yeah, I mean, it's something that we could explore in the future.
Thank you.
And would be really interesting.
Yeah, hi, great talk, very interesting. If I remember rightly, your ZZ interaction is like an order of magnitude smaller than what D-Wave has. Is that a problem? Is that an issue? Do you care? And
I mean,
what sets this magnitude? Could you change that, make it bigger? Or?
Yeah, we could. This was like a first prototype, and we decided to not have a super high ZZ interaction because in order to characterize the device, it's easier if the interaction is not that big. Because while designing these, we are also developing the tools for characterizing the device. So our first goal was to have something like this that we could characterize easily and then scale it up, like scale this interaction. Because of course, getting to a point in which you are able to apply these algorithms is not easy. There are many steps that you have to do before. And it's easy to characterize the system with smaller coupling strengths.
But to make this bigger, you presumably increase the circulating current in your coupler or something like that. Have I understood that correctly?
Like, we can do that by, I mean, you can do several things. I think that the one that has more impact is like modifying this inductance that connects the qubits to the coupler.
Okay, thank you.
Last question.
Tim has a comment.
Our energy scales of the qubits are much lower.
Okay. You mean delta, the transverse field?
Okay, very nice talk. Can you, because this could solve the problem of having more coupling, can you do Floquet driving on the qubit to rotate the interaction? Because this in cold atoms is, there are protocols for doing it. So maybe it's something you may look at.
Yeah, I mean, I'm not an expert in this kind of driving, but I know that people in the team are exploring these kind of things. So yeah, they are telling me yes.
Okay, let's give one last applause to Andrea. And